Okay, so in this lecture, we are going to talk about uh, the energy considerations when we are designing a brake or a clutch. Okay, so if you look at this figure, uh, we've already stated that um, that when you apply a clutch or a brake, so what happens is that with the application of a brake and a clutch, basically there is some kinetic energy. Um, if it is a brake, then kinetic energy needs to be absorbed because there is slippage over here, or the kinetic energy of the moving body needs to be absorbed. If it is a clutch, in order to have omega 1 equal to omega 2, again there is some energy, kinetic energy, that needs to be absorbed. And in the case of a brake or a clutch, this energy appears in the form of heat in the brake or in the clutch, right? So initially, if we have some temperature of the brake or the clutch, this temperature is going to rise up, right? So this temperature is going to go up and rise. Now, let's say uh, over here in this figure, if you look over here, um, let's say that if this is omega 1 and this is inertia I1, inertia I2, and this mass is rotating at omega 2. So the equation of motion, which is equivalent to F is equal to ma, we can write that the torque, which is T, is will be equal to I1 theta double dot 1, where this is the angular acceleration. So for the first one, that is going to be I1 theta double dot 1 equal to minus T. And since we are applying brakes or clutches, so the torque acting on both the shafts are going to be opposite to each other. So the next one will be T, or you can either take this one negative and this one positive. So that will be equal to I2 times theta 2 double dot. So these two are the equations of motions for this shaft 1 and shaft 2, okay? Or mass 1 and mass 2. Now, we can find out the velocity, uh, which will be if we take this equation and differentiate this equation uh, with respect to time. Okay? So differentiate this with respect to time t. So from this, let's take this I1 to the other side. So we'll have theta double dot 1 equal to minus T over I. And if we differentiate this with respect to time, what we are going to get is theta 1 dot um, theta 1 dot equal to minus T over I1 times T, because we are differentiating with respect to time T, plus the constant of with differentiation, which is omega 1. Similarly, I can get the velocity um, of from equation B by differentiating this equation, that is theta 2 dot equal to T over I2 times T plus omega 2. Now, initially, if if I put t equal to 0 in this equation. So my theta dot 1 is going to be equal to minus t over I 1 times t, which is going to be 0. Okay? So this is going to be 0 because t is equal to 0. ठीक है? This initial time, since I say t equal to 0 plus omega 1. So initially my theta 1 dot will be equal to omega 1. And similarly from this equation, at time t equal to 0, my velocity initially, that is going to be equal to omega 2, and then after application of brakes or clutches, the velocity is going to change, and that omega 1 will go to some velocity, or omega 2 will go to some velocity, and let's call that steady velocity omega. Okay? Now I can find the difference between these two velocities, which is theta 1 dot minus theta 2 dot, and let's call this, we can also call this a relative velocity, right? So we can also call this relative velocity, which will be theta dot. And if I take equation C and subtract that, subtract equation D from this, which is theta 1 minus theta 2, which will be equal to T over I1 times T small t plus omega 1 minus this whole thing, and that's going to give us omega 1 minus omega 2. So omega 1 minus omega 2 and t times I1 plus I2 over I2 I1 times t. So this is going to be the difference between the two velocities, which is theta 1 dot minus theta 2 dot. Okay. So this is the relative velocity. Now, let's say if if we take time t to basically um, reach the to cover the velocity difference, we can actually find that out, and that will be equal to that time t1 will be equal to I1 I2 times omega 1 minus omega 2 over t times I plus I2, right? So and that's from this above equation that we can go ahead and find that. Now um, the energy dissipation is going to be, yeah, or the energy is going to be U, right? And we know that that will be equal to tau TV, right? Which in general, but over here it is going to be T theta dot, right? Which is the difference between the two velocities. And I can go ahead and put the values of t theta dot. So t, and putting the value of theta dot, which is omega 1 minus omega 2 minus t times I plus I1 plus I2 over I1 I2 from this equation, right? So so now I can integrate this equation and find the energy uh, during the operation of the brake or the clutch. So that will be from initially from time t equal to 0 to time t1. So that will be equal to u dt. Okay? I'm going to integrate this with respect to time. So that will become t, and then integral from 0 to t1. and putting in the value of u over here dt. And if I integrate that, my E is going to be equal to I1 I2 omega 1 minus omega 2 square 2 I1 plus I2, 2 times I1 plus I2. Now, the heat and energy conversion is E over, sorry, that is E over 9336. So if I have want to if I have heat, and that is equal to E over 9336, or my E is equal to 9336 times H. Okay. Now, let's see. So, what would happen that when you apply brake, and due to that slip, the temperature is going to rise. But we have how does the temperature rise? It depends on what material you use. Um, for example, we have H equal to um, W CP times delta T. You are very familiar with this equation where Cp is the specific heat capacity in BTU pound per degree F. Delta T is the temperature difference, which in this case will be the temperature rise. And W is the mass of the clutch or the brake parts. So basically, you might be familiar with another version of this equation, which is MCP T2 minus T1, or MCP delta T. But this is the same equation. So you can find out the temperature rise by just rearranging this equation, where delta T is equal to H over Cp times W. Now, a if if we look over here, we can or we can also write, as I said, that we can also write this in terms where delta T is equal to E over CPM. If we use the units of centigrade for temperature, and Cp is in joules per kg degree C, um, which for steel is given over here, and it is 0.12 for steel or cast iron, in BTU per pound mass degree F, or it is 500 joules per kg degree C for the same steel and iron, where M is the mass of the clutch or the brake parts in kg. So we can similarly, we have another equation which is known as the Newton cooling model. And the Newton cooling model says that T minus T ambient, which is the temperature of any T, which is temperature at time T, temperature at time T, minus the ambient temperature divided by T1 minus T ambient, where this T1 is the initial temperature of the brake or the clutch that we are going to use, will be equal to exponent of HCR. What is HCR? HCR is basically the coefficient, it is the combined coefficient of heat transfer, or the overall coefficient of heat transfer in BTU per inch second degree F. A is the area from which heat transfer takes place. W is the mass of the object, and Cp is the Cp is the specific heat capacity in BTU pound mass degree F. So so for this is the Newton's law, Newton's cooling model. Now, how does this apply to brakes and clutches. Let's see. If you look at this figure, this is the instantaneous temperature T1, sorry, Ti. And over here on this axis, this is the time um, time t, right? So let's say at first we have the temperature of the brake or the temperature of the clutch equal to the ambient temperature. Now, when you apply a brake, what is going to happen is that heat is going to be generated by the application of the brake or the clutch, and it is going to rise the temperature of the brake or the clutch, which will go to T1. Now, um, so with the passage of time, heat is going to transfer. So this is the temperature rise basically, which is T1 minus T ambient or T infinity or T environment. So with the passage of time, what is going to happen is that the brake or the clutch is going to cool down, right? Um, until you happen to apply another brake, or if you do not, then it is going to cool down to some temperature over here. But generally, what happens is that you might have you might need to apply a brake or a clutch. If you are moving in a car, you do that frequently, and your temperature is going to go up to T2, right? So you will reach another um, temperature, and there is again a temperature rise, and there should be some heat transfer till you apply another brake. But if you keep on applying brakes, the temperature of the brake or clutch is going to go up and up and up, and it might reach such a value that the brake or the clutch is going to cease, or it will not perform its function. So what we need to do is that we need to design a clutch or a brake from which heat transfer should take place. At least the amount of heat loss from the brake or the clutch should be equal to HCR. What is HCR? HCR is the overall heat transfer coefficient. We already discussed something like this in bearings, times area. Since the amount of heat loss is proportional to the area times the temperature difference, right? So the temperature difference is that if this is any temperature T minus the ambient temperature, that is going to be the effective temperature difference for the heat transfer. So that times area, and if we replace the um, the proportionality by equality, so we are going to put HCR instead, and that will be equal to HCR A times delta T, right? So now we can also write this HCR as HR plus FVHC. Now, why are we writing it like this? Actually, your HR is the heat transfer coefficient for or the radiant component of the overall heat transfer coefficient. So this is for radiations. Um, the HC is um, for convection, and the FV is basically the ventilation factor, which we already talked about in bearings, but that was in a different context. But still, it has something to do with forced convection. Forced convection means that if there is air passing through the component, it is going to speed up the convection, and this Fv is basically Fv depends on the velocity of the air, or the speed of the air at which it comes in contact or and passes over the component. If you look at this figure, you can read from this chart Hc or HR, right? At different temperature difference for different temperature difference in still air. These are the contours for for HR, and this one is for HC. So the radiation part and the convection part. But if there is air moving or there is forced ventilation, then the HC, which is the convective heat transfer coefficient, that should be multiplied by FV. And let's say, for example, the if the air is moving at 20 foot per second, then you have to multiply the HC by 4. Similarly, if it is 40, you have to multiply it about 5.9, and so on. So that will enhance the amount of heat transfer. Now, if we are talking about a break, again, the heat that will be generated is equal to, since this is half, this is the energy, and that is the velocity difference, which is half um, um, I half I omega naught minus omega f square. This is the initial and the final velocity, or the original and the final velocity, times I, which is equivalent to mass. Okay? So that is the kinetic energy is half mv square. So this is half I omega naught square minus omega f square divided by the conversion factor to from heat to energy and energy to heat. So your basically your delta T is equal to E over WC. If we set T min minus T ambient, or T max minus T ambient equal to exponent of minus beta T1. This is actually the same equation as this one, which is equation 16-56. The only difference is that we are calling this one and this one with T minimum and T maximum, and the value we are using just a short form of the above equation by saying that this it is to the using beta, where beta is that um, beta has a value of let's see, beta has a value of minus HCR times A over WCP, and multiplied by the time T, right? So multiplied by the time T here. Now, so we can find out the maximum temperature that which will result in when we apply the brakes or the clutch, that will be equal to T ambient plus delta T over 1 minus exponent of minus beta T 1. Now, though this equation does give us somehow an idea of how much the temperature is going to rise, but there are other factors too that this might not agree with the experimental data, but still it gives us information that can be very useful, or the from which at least we can measure the performance. Basically, this is the performance parameter for the clutch and the brake, that the temperature should not go really, really high so that it will not perform its function. Now, looking at this problem, it says that a caliper brake is used uh, 24 times per hour to arrest a machine shaft from a speed of 250 revolutions per minute to reset. The ventilation of the brake provide mean air speed of 25 um, 25 foot per second. ठीक है? And the equivalent rotary inertia of the machine as seen from the brake shaft is 289 pound mass. So I is given. ठीक है? your एफ वी जो आप इससे कैलकुलेट करेंगे, that velocity is given to you, the speed is also given, and the number of times that the brake is used. The disc is steel with a density of 0.25 pound mass per inch cube. So the density of the steel for the disc is given to you, and the specific heat capacity is also given, which is C. The diameter of 6 inches and the thickness of 1 by 4 inches, and the pads are dry sintered metal. ठीक है जी? The lateral area of the brake surface is 50 inch square. So A is also given to you. Find T max and T minimum for steady operation of the brake. ठीक है जी? So we can go ahead and first of all, find the time t, as it says that the caliper brake is used 24 times per hour. So that means that t, which is the for the application of the brake, that is 60 um, square by 20, that will give us time t1 24 times, so that is 150 seconds. Assuming that the temperature rise T max minus T um, ambient is equal to 200, we are assuming this from figure 16-24. We can go ahead and find our HR and HC, which is the radiation heat transfer coefficient and the um, convective heat transfer coefficient. Also from 16-24b, your ventilation factor, which is 4.8 for a velocity of 25 foot per second. So go ahead and find your HC, the combined heat transfer coefficient, by incorporating these values. Okay? So it turns out to be 12.6 into 10 to the minus 6 BTU per inch cube second Fahrenheit. The mass of the disk can be calculated because we know the dimensions. We also know the density. So it will be pi by 4 d square times h times gamma. We know the density, we know the diameter, and we also know h. So that turns out to be 1.99 pound mass. Now the energy that is going that we are going to have in terms of heat, that is going to be half I 93 over 9336 W A square minus W F square, the initial minus the final velocity. So putting the values in there, it turns out to be 10.6 BTU. Go ahead and find your beta by putting all the values. Um, we got beta. We have a relationship for delta T, which is E over W times Cp. So that is your temperature difference, 49.3 degree F. Go ahead and use equation 16-60 to calculate your T maximum, which is 160 degree Fahrenheit. Now the predicted heat transfer here, the temperature rise would be T max minus T ambient, which is 139 degree F. Um, you can also, iterate with revised value of HC and HR and can make the solution converge to T max of 220 degree F at T minimum equal to 171. If you and so that's what they wanted, that they wanted us to find out T max and T minimum, which have these values. Now, these are some tables that gives you the area of the friction material for average breaking power. This table, area of frictional material for a given average breaking power. The duty cycle, if it is frequent, infrequent, intermittent, or heavy duty. Typical applications are emergency brakes. For infrequent, it is emergency brakes. For intermittent, elevators, cranes, winches, heavy duties, excavators, presses, and so on. So for different types of brakes, this is the ratio of the area to average braking power is given to you from this table. So if you have to design any of these brakes, you would consider this. Now, these are the characteristics of some frictional material that you would use. For example, in the previous example, we used the sintered material, which was dry. So these are the coefficients of friction, the maximum pressure, the maximum instantaneous temperature and continuous temperature that it can withstand, and the maximum velocity. The application for these material is also listed in this table. So have a look at this. And again, some properties of braking lining, different materials. For example, woven lining, molded lining, and rigid blocks. These are given to you. What will be the maximum? What is the compressive strength, the tensile, the maximum temperature, and all these are listed in table 16-4. Frictional materials for clutches are listed in table 16-5 with all the properties that you would need for design. We already talked about positive clutches, but as I pointed out in the previous lecture, that the characteristics of these positive clutches is that there will be no slip, no heat generated, and but the problem is that they cannot be engaged at high speeds, and sometimes cannot be engaged when both shafts are at rest, because they might not be aligned with each other. So engagement is accomplished by a shock. And again, when you engage these, for example, this is a square jaw clutch. This square jaw clutch, if you look over here, this part goes in here, and this part goes in here, and it is going to engage with this. But if it is engaged at a speed, there is no slip or no gradual engagement, but it engages suddenly, and there's going to be a shock. Okay. I guess that should be it for